Welcome to this lecture on the housefly as a mechanical vector. Have you ever wondered how a simple fly landing on your food can make you severely ill? Today, we're going to explore the fascinating and slightly gross biology behind how the common housefly transmits deadly diseases without ever getting sick itself. We will build our understanding from the ground up, looking at the anatomy of the fly, the diseases it carries, and even the mathematics of how long bacteria can survive on its body. Let us dive in. To start, let us build an intuitive understanding of what a mechanical vector actually is. Imagine you are cleaning up a messy, muddy garden. Without washing your hands, you immediately go into the kitchen and start preparing a fresh salad. The mud and bacteria from the garden would physically transfer from your dirty hands directly onto the clean food. This is exactly how a housefly operates in our environment every single day. It acts like a tiny, flying, dirty sponge that lands on feces or rotting garbage, picking up millions of invisible germs on the outside of its body. When it subsequently lands on your uncovered food, those germs simply fall off or are washed off into your meal. The fly does not get sick, nor do the germs grow inside the fly. The insect is merely acting as a living taxi service for disease. Now that we have a conceptual picture, let us look at the formal scientific definition. In medical entomology, a mechanical vector is defined as an organism that transports a pathogen from a source of infection to a susceptible host, but with one crucial condition. The pathogen undergoes absolutely no biological development or multiplication inside the vector. The vector is purely a physical transport mechanism. The common housefly, scientifically known as Musca domestica, is the ultimate example of a mechanical vector. Because the pathogens do not need to incubate or develop inside the fly, the transmission is immediate and highly effective the moment the fly moves from filth to food. This brings us to the biological mechanism itself. Why is the housefly such an efficient mechanical vector? It all comes down to its unique anatomical features. First, it possesses a highly hairy body that easily traps microscopic particles. Second, it has specialized foot pads called pulvilli. These pads secrete a sticky substance that accidentally glues bacteria and viruses to its legs as it walks over contaminated surfaces. Furthermore, the housefly has sponging mouthparts. It cannot chew solid food. Instead, it must vomit digestive juices onto the food to liquefy it before slurping it back up. This constant cycle of walking on filth, picking up pathogens externally, and regurgitating stomach contents onto human food makes it a highly efficient mechanical transmitter of disease. Before we move on to the diseases they cause, let us see this anatomy with a concrete visual example. Here we have a detailed diagram of the housefly. Notice the dense hairs covering its body and legs, which act like a net for microscopic debris. At the front, you can see the sponging mouthparts, or proboscis, with a droplet of regurgitated fluid. This is how it liquefies its meals, contaminating whatever it lands on. Now look at the magnified circular inset focusing on the foot. These are the pulvilli, the sticky foot pads we just discussed. You can clearly see how bacteria and pathogens physically adhere to these pads. Every time the fly lands, it leaves some of these hitchhiking pathogens behind. Now that we understand how the fly operates, we must look at the real-world consequences. Understanding the housefly's role as a mechanical vector is absolutely critical for global public health and sanitation management. If we did not recognize how these insects spread disease, we would suffer from continuous, unexplained outbreaks of severe gastrointestinal illnesses. Houseflies are directly responsible for mechanically transmitting the pathogens that cause devastating diseases like cholera, typhoid fever, bacterial dysentery, and salmonellosis. By knowing exactly how they carry these pathogens on their feet and mouth parts, public health officials can design effective interventions. Improved waste management and strict food hygiene protocols block their access to human food, which ultimately saves millions of lives, especially in developing nations with poor sanitation infrastructure. This biological reality leads us to an important mathematical question. How long do these pathogens actually survive on the fly? When a fly leaves a contaminated area, the bacteria on its legs do not survive forever. They slowly die off due to drying out or ultraviolet sunlight. We can represent this survival over time using a standard exponential decay formula. The formula is n of t equals n0 times e to the power of negative kt. Here, n of t represents the number of surviving pathogens at a given time t. N0 is the initial load of pathogens the fly picked up. The variable k is the decay constant, which tells us how quickly the bacteria die off. If k increases, the bacteria die faster. Finally, t is the time elapsed. If the fly reaches your food in a very short time t, the surviving bacteria remain dangerously close to the initial load. Before we move on, let us see this formula in action with a concrete example. Suppose a housefly lands on animal waste and picks up an initial load of 10,000 cholera bacteria. The decay constant is 0.1 per minute, and the fly takes 5 minutes to reach your sandwich. We want to find how many bacteria survive. We start by substituting our known values into the exponential decay formula. The exponent becomes negative 0.5, representing the total decay factor over the flight. Evaluating e to the power of negative 0.5 gives us approximately 0.6065, meaning about 60.65% of the bacteria survive. Multiplying this fraction by the initial 10,000 gives us a final count of 6,065 live cholera bacteria deposited on your food. This is more than enough to cause a severe infection. Now that we have calculated the risk from a single fly, we must consider a more realistic picnic scenario. Sometimes the danger comes not from one single fly, but from multiple flies landing on your food over the course of a meal. Even if a single fly has a relatively low chance of transmitting enough pathogens to make you sick, allowing multiple flies to touch your food drastically increases your overall risk. Because each fly acts independently of the others, every single landing is a new chance for an infectious dose to be deposited. To truly understand this risk, we need to look at how these independent probabilities compound mathematically. This brings us to the mathematical model for multiple exposures. The formula to calculate the total probability of getting sick from multiple flies is capital P equals 1 minus the quantity 1 minus lowercase p raised to the power of n. In this equation, capital P is the total probability of getting sick from the combined exposure. The lowercase p represents the probability that one single fly transmits enough pathogens to make you sick. Finally, n is the total number of different flies that manage to land on your food. As the number of flies, n, increases, the term being subtracted becomes smaller, which physically means your overall probability of getting sick, capital P, grows rapidly. Let us apply this formula to a real scenario. Suppose the probability that a single fly makes you sick is 0.2 or 20%. During a picnic, 4 different flies land on your lunch. We want to calculate the total probability that you will get sick. We substitute p equals 0.2 and n equals 4 into our formula. First, we calculate 1 minus 0.2, which gives 0.8. This is the 80% chance a single fly does not infect you. Next, we raise 0.8 to the fourth power, giving 0.4096. Finally, subtracting this from 1 gives a final probability of 0.5904. This means you have a 59% chance of getting sick, showing how quickly the danger escalates. Now that we have used this formula, let us understand where it comes from. Instead of calculating the probability of getting sick directly, which is mathematically complicated, it is much easier to calculate the probability of not getting sick from any of the flies. We start by defining P as the probability of getting sick from one fly. Therefore, the probability of not getting sick from that single fly is simply 1 minus P. Because the flies act independently of one another, the events do not affect each other. To find the chance that you stay completely safe after multiple landings, we must multiply these individual safety probabilities together. This sets up the foundation for our final equation. Continuing our derivation, we take that single fly safety probability, 1 minus p, and multiply it by itself for every fly that lands. For n flies, this means raising 1 minus p to the power of n. This term, 1 minus p to the power of n, represents your overall chance of escaping the picnic without any infection at all. However, we want to know the probability that you do get sick. Since you either get sick or you stay healthy, these probabilities must add up to 100%, or 1. Therefore, we subtract the combined safety probability from 1. This gives us our final proven result, capital P equals 1 minus the quantity 1 minus p raised to the power of n. This mathematically proves why keeping all flies away from food is a critical hygiene practice. To conclude, let us review the most important ideas we have covered. First, houseflies act as mechanical vectors, physically transporting deadly pathogens from filth to our food without the bacteria developing inside them. Second, their unique anatomy, specifically their hairy bodies and sticky foot pads, makes them incredibly efficient at this dangerous job. Third, we learned that pathogen survival on the fly can be modeled using exponential decay, proving that flies carry live bacteria even after long flights. Finally, we proved mathematically that allowing multiple flies to land on your food drastically increases your risk of infection. You now have a complete biological and mathematical understanding of why strict food hygiene is essential to protect public health.